Gilly with Lab 1 constant velocity. So the purpose of this lab is to observe the motion of an object moving at a constant velocity and compare it to a computational model that demonstrates the same motion in ideal conditions. The lab will use this comparison to examine the validity of Newton's second law, also known as the momentum principle. So by ideal conditions, it means that there are no external forces or surroundings present in the experiment. And the reason we're making this comparison between the actual model and the computational model is because the computational one assumes the ideal conditions for the experiment and thus creates an example of how the motion should work in theory and in accordance to Newton's second law. So for this experiment, the system is the marker and surroundings is everything else that's not the marker, including the table, meter stick, etc. Fundamental concepts discussed in this lab is Newton's first law, which states an object at rest will remain at rest and an object in motion will remain in motion unless acted upon by an external force. The momentum principle, which states a change in an object's motion is directly proportional to the net interaction between a system and its surroundings. And these concepts are applied in this lab because when there are no external forces acting on the system, the object remains either at rest or in motion and thus moves with a constant velocity. So the lab examines an object with a constant velocity to verify these two laws, which will be shown here, that this is the equation for each of the principles. So for momentum principle, the net force is equals the change in momentum with respect to time. And in the situation that there are no external forces or F net equals zero, you can see it turns into Newton's first law where the final velocity equals initial velocity, meaning the object's either at rest if it equals zero, and if it's a non-zero, it's moving with a constant velocity. So the position update formula also gives that you could take the average velocity to be the initial velocity when external forces, net forces equal zero. So the procedure of the experiment is that record a video of an object moving with a constant speed in the same direction, so the marker, importing the video onto the tracker software to track the ball's position at set time periods according to an axis defined in the software, creating a computational model of the ball's position according to the same axis defined in the software, and serves as the ideal motion of the ball in ideal conditions, and importing the data into Google Sheets to create a graph modeling the actual motion and predicted motion for analysis and comparison. So the tracker software looks like this. And we take the data from the tracker software to find the initial velocity, which is the average velocity, and then we take that to be 0.606 meters per second in the x direction. So then the next part is to put it into the code, which was basically two parts. So we define the initial conditions to create an ideal model of the motion based on actual conditions of the experiment, and then create an ideal model of motion for prediction and visualization using the momentum principle. And then this is what that looks like. So the graph that we took by putting the data into Google Sheets and then making a graph, you could see the similarities is that the positive slope, both of them have a positive slope, which means that they both have a positive velocity. And in the beginning, you could see that the slopes are really similar, so that's that. And then the difference is that the model position, which is the red line, is constant while the actual line starts to fall off at the end, which suggests that there is some external forces, whether that be friction or something else, that's slowing it down so it can't reach that position as the model one. And the model positions are consistent, have consistent differences, while the actual positions are they don't have consistent differences, which makes it not aligned. So possible error is in the tracker software that acts as scaling center of marker. So marker positions and 1 meter calibrations might have not been accurate due to human error, and then the assumptions of like the ideal conditions are not true in the actual experiment because the marker was pushed with an initial velocity, but it ended up slowing down, which we saw in the graph because these assumptions are not true. So if the x-axis were changed, the object would simply have like the motion would just have a negative velocity, and then we have known forces. So we have force due to gravity on Earth, normal force acting upward on the marker, and we could tell there are unknown external forces by the graph of the tracker analysis. And we have unknown known forces such as like friction and air resistance, and we have unknown forces, which is any forces acting on the system that we don't know. So the answer to this question is that no, we cannot say for sure how many forces are being added together.